Welcome back. This is lesson 10 of Machine Learning Zoomcamp session 8. And in this lesson, we will talk about creating more data from the existing data. In the previous lesson, we talked about dropout, which is a way of regularizing your neural network. And the problem we talked about that if for our neural network, we go over the same data point, the same picture many times, let's say 10 times, then our neural network sees the same image with, let's say, a logo, a circle, and a logo inside it. It may think, okay, if I see this logo, it must be a t-shirt. And this pattern doesn't necessarily hold true in case of all the objects, in case of all the clothes. We talked about dropout as a way to solve this and sort of hide a part of the image from the neural network. Every time it sees an image, we kind of hide a part of this. And there is a different way of addressing this problem. So in case of dropout, we would freeze a part of a network during training, but there is a different approach for solving this problem, which involves generating more images from existing ones. So let's say if we take our image, then from this image, we generate 10 more different images. So then the neural network will not see exactly the same image every time. Actually, there are many different things that we can do to generate more images from existing ones. There are simple image transformations that we can use to generate more data. First of all, let's say we have this image and we want to generate more pictures from this. There is one simple thing that we can do is we can just take this image and flip it. So these are image transformation. First thing we can do is we can just take an image and flip it. We can flip it horizontally and vertically. I will not use the t-shirt here because I cannot flip it in this app. I will just draw it. So let's say we have a letter R. So what we can do is we can flip it. So it will be sort of like mirroring. This would be, I don't remember if it's vertical flip or horizontal flip, but basically we take this image and flip it. Then we can flip also along this dimension. This would be, I guess, horizontal flip, not sure, but then our R will be upside down. That would be a different way of flipping. Actually, I have some code for generating these transformations. Let me show it to you. So in Keras, there is this image data generator. Remember, we talked about this image data generator actually can generate these augmentations. There is some code for doing this. It lives in this apply affine transform. So I took it out and then I put this in a notebook. I will not execute this. I will just walk you through the notebook. You can find this notebook in the repo we use. I did this for creating illustrations for the book. It lives in chapter 07 neural nets, and then the file is augmentations. So the notebook is augmentations. And here I used this apply transform function from Keras. I took it and I created another function augment that uses this one. But actually internally it uses this apply affine transform. This is just more like a wrapper around this. But I took all this code from Keras. So it's not something I wrote. So I took it. I don't remember exactly from where, but I think it's not that difficult to find. So this is just some helper code to see the transformations. And then I use the t-shirt that we also use in the examples. And the first transformation here that I have is the flip. The first flip is horizontal. So we are doing this along this dimension. This is like a horizontal line and we're flipping along this line. So I think that's why it's called horizontal. And then vertical, we have a line here and we're flipping around this line. And then when we do both, I think it is the same as rotating the image by 180 degrees. So these are the kind of transformations we can do. Of course, this transformation for our data set doesn't make much sense because all the images we have in our data set, they're always aligned like that. And if they aren't, I remember processing these images and making sure that if they're upside down, I rotate them so they're not upside down, basically. So transformation like that doesn't make much sense for our particular data set. For some data sets, it does, but not for us. Then the next transformation is rotation. We take our image and we rotate it. So we can rotate clockwise or counterclockwise. So our image still has to be squared. So this would be our image. So we will need to cut out all these parts. We remove them and somehow need to fill these parts. So it still looks like an image. And the same happens here. We kind of lose a part of the image, but it still stays 150 by 150. So The original one, let's say, is also 150 by 150, but we rotate it. Actually, in the data set that we have, some of the images are not always positioned perfectly. So sometimes there are slight variations, slight rotations. So maybe for our data set, it actually makes sense to generate images like that. In Keras, we can also do this rotation transformation, and the parameter for this transformation is the number of degrees, how much we rotate. And you see it can be positive and it can be negative. So when it's negative, we rotate counterclockwise by 30 degrees. And you see the actual image was like that. What Keras did, it took this out, cut these corners away, and then it made an educated guess how exactly it should pre-fill these corners. So I think it took whatever pixels were there and just kind of extended them. No, and the same here. Here it's counterclockwise, and when it's positive, it's clockwise. So here we rotate by 30 degrees as well. Then another transformation we can do is shifting the image. Let me just write it here. We can shift. So again, let me take this image. I need to move to another slide. So let me copy it here. We have our image here, and the transformation we can make is shifting it a bit up or down, or left and right as well. So let's say our image is here. We cut out this part or this part, and whatever is left we use as our image that we feed to the neural network. We can move things horizontally or we can move things vertically. So this is how we do this in Keras. So in Keras we specify, so when we say we want to shift it, like it's called height shift, let's call it vertical shift. Basically we are moving along this dimension. So when it's negative, we're moving it down, and then it's positive, we move it up, and then you see this is the image. And we move it like 30% down. So we cut this part away, cut it out. And then here we take this line and repeat it. Yeah. So this parameter here is like how much we put it up or down in percent. And the same with width shift. Instead of moving it up or down, we move it to the right when it's negative, and we move it to the left when it's positive. So this is shifting. Then another augmentation, another transformation is shear. I'll use again the letter R because I cannot do this shear transformation here with this image. And imagine that we take this corner, kind of pull it down. We pull down only this corner, but we don't pull this one. And what happens is we have something like this. Our R looks like that. So we're kind of pulling only one side of the image. So we can do it like that, or also in the other direction. So if we, instead of pulling it down, we take this part and pull it up, then the R will look something like that. This is shearing transformation, and you see that it's different from rotating. So in case of rotation, so let me show you. So in case of rotation, we actually rotate, we don't just pull it. So they might look similar, but they are a bit different. So again, in case of shear transformation, so it can be positive and negative and positive. This is like either you move this corner up or this down. Then you can zoom in and zoom out. So here we have an example that we just shrink. This is our image, and we shrink it only along the X dimension. So along the Y dimension, it's not zoomed, so it stays as is, but we kind of shrink it. So actually, you see, 1 is not transformation at all. 2, we shrink it 2 times. 4, we shrink it 4 times. If it's below 1, then we are kind of pulling it. The actual image is like that, and we're just cutting out this. And in case of when zoom is 0.24, so we're kind of pulling it 4 times. So the image maybe looks like that, and we are cutting this out, and we're leaving only this part. We can do the same for the Y dimension. We can shrink and zoom. Let me just write it here. So let's say in case we zoom in, we only focus on this part of the image and we cut out the rest. So this we zoom in, right? And we can also zoom out. So then we have an image, and let's take this one. We'll put it in the center. We need to pre-fill what is around. So we can zoom in and out. And as you saw in Keras, we can zoom in only along one axis. So we can zoom in along the x-axis or y-axis. There are actually many other things we can do. Can play with brightness or contrast. And remember when we talked about dropout, we discussed that we can just have a black patch and just randomly put it on an image, and that would hide a part of the input, a part of the image. Actually, even though we use this as for illustrating dropout, and dropout doesn't really do this, but we can have the same effect. We can achieve the same effect. And putting this black patch on an image is actually also another augmentation, data augmentation that we can do. I don't know if Keras out of the box can do this, but there are libraries that actually have these data augmentations. And there are many, many more things. And what is more, you can take all these and combine them. So they are all combinable. We can shift and shear and zoom and change contrast at the same time. I mentioned that we can combine them, and this is an example how it's possible to do it. So you see this case, it was slightly rotated. Yeah, so this one was rotated and flipped. So this one was rotated a bit. This, I think we applied shear transformation here. So you see every time we get a slightly different image. It's still all the same image. It's still a t-shirt, and you can see that the shape of the t-shirt is almost always preserved. Like it's just a little bit different. There are many different ways how you can put a t-shirt in your floor and then take a picture. It's not always ideally positioned. So here we're kind of modeling this situation. So I used image data generator, and it has a bunch of parameters. So rotation range, width, height, shear, zoom, and so on. So we can actually just take this image data generator and use that for training our model. Let me just open the code. So remember, this is how we created data sets for our models. So we had this image data generator, and then we read from train data set, and then we did the same for validation. So now we need to take that and we need to change the image data generator. You see here, this is what we used. So we used image data generator, and it has a bunch of parameters that we can specify to do data augmentation. So now let me copy it. Copy two things at the same time, both training and validation. So now what I need to do is specify some parameters in this image data generator. There is a lot of things, so shear range, zoom range, and for us, we are interested in this rotation range, width shift range, height shift range, brightness range, maybe not so much. I didn't experiment with this one, but there is a bunch of parameters that we can use. So let me just copy them. I'll remove. So these are potential things that we can experiment with. For example, if we put 30 here, it means that we want to generate images that are rotated randomly. The rotation degree is chosen in the range between -30 and 30. There is an image, and we can either rotate it by -30 or 30 or by 10, -10, 10, 0, or any number between. So it just selects a number randomly between -30 and 30 and rotates by this degree. Then the same here for width shift range and height shift range. Let's say if we put here 10 and here 10, it would use a range from -10 to 10. And I think this is inclusive. So here for rotation, it's also -30, 30. So the square brackets here, it means it's inclusive. So -30 can also be there, I think. But yeah, it doesn't matter if it's maybe 29,999. It's as good as 30. Anyway, for width and height shift range, we can say that we want to shift by 10% of the image, either -10 or 10. Then zoom range. So in this example, we zoomed only by X or Y dimension, but I think here we just specify, actually, I don't remember how it actually works. So where's zoom range? Yeah, if we just give one number here, so let's say we say 0.1, it means that the range for this would be 0.9 to 1.1. 1 here means do not change the zoom at all. So image stays as is. 0.9 means I think enlarge it a little bit. So zoom in, and when it's larger than 1, we are shrinking it. So for example, we can say it's 0.1. and then shear 10, for example, and then horizontal flip. I forgot what horizontal is. Yeah, so horizontal flip is not interesting for us because it turns the t-shirt upside down. We're only interested in vertical flips. So we can say we want to do vertical flips as well. And now you see all these parameters and you might be wondering, like, how do I choose which parameters I need and which I do not? So we can talk a bit about this. First, we just need to use our own judgment. If we want to apply an augmentation, does it make sense? Like in our case, does horizontal flip make sense? Not so much, because all the images we have in our data set, they are always positioned correctly. So we don't have images that are upside down. And it's actually true for both validation and testing. And this is the kind of data we expect to see in the future. So let's say if we don't expect to see t-shirts turned upside down when we apply the model, then we don't need to generate this kind of augmentations. But vertical flip, it kind of makes sense because clothes usually is symmetrical, like hats, shoes, basically everything, like all the clothes we use. Most of them look symmetrical, so I think the vertical flip makes sense for this one. As I mentioned, so we look at the data set and we see what kind of things make sense. This is also what you can do, and this is what you should do, is you can look at the data set and see what kind of variations you have in the data set. Let's say you look at the images and you can ask, are objects always centered or not? If they are not, then you can think about shifting or rotation, like maybe they are rotated a little bit in the data set, or maybe they are shifted, so they are not always in the center. So then use rotation or shift. And the last thing that we should remember that augmentation is also a hyperparameter of our model. Often we just need to try different augmentations and see what works and what doesn't. You can think of this as, should we add another layer or not? Should we add dropout or not? And then should we add rotation or not? So then you just take your data set, add rotation, train for multiple epochs, and you compare it with the same model but without rotation and see if your score on validation improves or not. So train it for multiple epochs. For example, what I sometimes do is I train it for, let's say, 10, 20 epochs, and then see, is it better than without this particular augmentation or not? So if it is better, then you use it. If it's no, like if it's, you see that it's strictly worse, then you don't use it. And if it's the same, you don't see significant difference, then you train for 20 more epochs and then train and then go to this thing. If after, let's say, 20 more epochs, you don't see that it's better, then you don't use it. So if it's the same or worse, you don't use it. If it's better, then you use this. So treat it as a usual hyperparameter. Okay, enough with theory. Let's actually do this. For this problem, I already experimented with augmentations, and the augmentations I selected, so rotation didn't help. Tried this, I didn't see any improvement. In fact, actually it got worse when I added rotation. With shifting also didn't help much. What helped was shearing for some reasons. Yeah, this is something I didn't think about, but then I experimented and I saw that it was 1% improvement, and then zoom range. And the last thing is vertical flip also seemed to help. So I apply augmentations here to the training dataset, but I do not apply the augmentations to the validation dataset. I leave the validation set untouched. The reason for that, it's random, right? So here we have this randomization component, and we want to have consistent results. So here, when we do validation, we still want to compare this model with the models we previously trained. And now if we start augmenting this data set, then maybe if we rotate slightly, our model becomes less accurate on validation, and then it messes up with our validation. So we don't change validation at all. So we always keep validation as is. We always use original images, because we can think of this as these would be the images that our users upload to our website. They will not use Keras to first rotate an image and then upload. They will just take a picture and upload it. So that's why for validation, we leave it untouched. We only change training. I think we decided that the best dropout was 0.2. Now let me copy this code as well. And now we actually need to, so let me train it for 50 epochs, because we First of all, we have dropout, which we use to regularize our neural network. And then now we also start adding data augmentation. So for the neural network, now it sees more images. So it requires more iteration because we're doing this. So let me train it for 50 epochs. We just run it. Actually, just as a remark, I checked this NVIDIA SMI tool, and I see that the GPUs are utilized not as good as when we don't do augmentation. And I think the reason for that is because generating more data from existing data, this is something that the CPU is doing on the computer, not the GPU. That's why for every batch, it first applies all these transformations before passing it to the network. And that's why our GPU is not always utilized at 90%. So sometimes it's 75, but we see that the utilization of a GPU is not great. So let's say we have a GPU and we have a CPU. So what happens in case of Keras? We first use CPU to generate augmentations, and then we use GPU to fit the model. And we do this at each iteration. You can see it here, every iteration here. So it's doing iterations. It's called steps here. It spends 300 milliseconds for each step. And if we look at the output before, so actually it spends less time per each step. We see now it spends 2 times more, so around 100 milliseconds here and 100 milliseconds here. This is the reason, first of all, it's slower, and second, that GPU is not utilized 100%. To avoid that, there are more complex things. So let's say you have multiple batches, like batch 1, batch 2, and this is more like just the theory because I'm waiting till the model finishes training. So I thought maybe for you it will be interesting. So if it's confusing for you, you just don't pay attention. Yeah, so let's say we have, this is our time. This will be our GPU, let's say, and this will be our CPU. So we use our CPU to do augmentation. And while we're doing this, nothing can happen. And then once augmentation is done, we do fitting on GPU. But what can happen in parallel is at the same time, we start augmenting batch 2. Because CPU and GPU can run in parallel while fitting the model on the batch 1. What we can do at the same time is prepare batch 2 on CPU. And then once it's prepared, finish fitting, and then we use this augmented batch 2 for fitting. So basically we know what will be the next batch and we are preparing it in advance. Keras doesn't do this, but there are ways of doing this. So they're a little bit more advanced. We will not be covering them here. So I think this TensorFlow data thing in TensorFlow, I think this is what you need to use to solve this problem in TensorFlow input pipelines. You can check it. I'm not really an expert in these things. I never used it. I just know it exists. And you can check this TensorFlow data to see how this problem can be solved. Let me see. It's still running. Okay. While waiting for the model to finish, I was having fun redrawing the slide a bit. Still running. Seems it finished. So let's see what we have here. Actually, the validation accuracy is quite bad. Perhaps I should have stopped this model earlier and not wait for 50 epochs. So let me print it since we have it. I'll just use this. History, don't have any label, just want to label validation. Let's also print training accuracy. Add legend. You can see that for training, it doesn't reach 100% accuracy. It's a bit more difficult to have very good accuracy. It's still improving. And now on the validation accuracy is like the best model we had was around 48%, and this is worse than what we had. So I'm not sure why. So maybe let me add smaller, less aggressive shearing, do something like that. In my experiments, in my previous experiments, that was actually the best set of augmentations, but I could have seen that that for this particular case here, it's not working already after 10 iterations. So it's still 77, so which is worse than what we had previously. So let me just rerun it with less aggressive shearing and let's see what happens. So as I see here, accuracy is not really improving. I am not sure why. This is strange. Let me just leave one augmentation and remove the rest. Now I will re-execute this. So the only augmentation I left is vertical flipping. I don't know what's going on. So let me try to remove augmentations at all. So I don't know if I got lucky when testing these things, or I am getting unlucky now a few times in a row. And actually, usually previously remember we were fixing the random seed to make sure the results are reproducible. With neural networks, it's much harder. So there are a lot of areas where a lot of moving parts that need randomization, and it's simply not really possible to ensure reproducibility here to fix the random seed. Yeah, you see, without flipping, it's better. I am really curious why. But yeah, okay, it seems we can do it without data augmentation. Usually it's helpful. Maybe I should just play with parameters, like maybe smaller learning rate, smaller dropout. I don't know, but yeah. So this is what we have. And remember that the best model we had was around 84%. I don't think we saved it. Yeah, so tuning neural networks is more art than science. So you just need to tune many different knobs and then have enough patience to see what happens. And then also maybe the learning rate I have here is not optimized, because we see in the images it starts jumping immediately. So maybe it should be smaller. But actually, if we think about this, the accuracy we had so far, 84%, this is sufficient for most of the use cases. And if sometimes our model says, hey, it's not shirts, it pens, or it's pens for shirts, it's not such a big deal. And this is where the model usually makes mistakes. So it confuses long sleeves with t-shirts. So of course, like we don't have a large data set for this. So this is an okay performance. So yeah, see here, we already have something like 80. And I think for now we have an okay model, sufficiently good model. And remember that we're still doing this on small images, on 150 by 150 images. What we can do now is, I will actually stop this. So what we can do now is take this model that we have and train it on bigger images, on images that are of 299 by 299 size. And I think there, when you have larger images, these augmentations make more sense, because actually you can see more details there. This is what we will do in the next video. So in the next video, we will train a larger model. It will be slower, but it will be more accurate. So see you soon.